All right, it's a pleasure today for us to have Jonathan Barmak from Universidad de Buenos Aires in Argentina, and he's going to be talking about star clusters in clique complexes and the Vietoris-Rips complex of planar sets.
Okay, great. Thank you very much, Facundo. So thank you, Henry and Facundo, for the invitation. I'm very happy to be in this seminar. So I will speak about a joint work with Martin Tancer. Let me begin with the definition of the independence complex of a graph. So for me, graphs will be finite and simple. So the independence complex is a simplicial complex whose vertices are the vertices of the graph, and the simplices are the independent sets of vertices. So by independent, I mean a set of vertices which are pairwise non-adjacent. Okay. So in this example here in this graph, we can see that A, C, and E, this is an independent set. Okay, none of these three are adjacent. So this will be a two-dimensional simplex in the associated simplicial complex. AD, again, they are non-adjacent, so this is also a simplex. EB, and you can check that this is the independence complex of this graph. Okay, it is easy to check that independence complexes are always clique. Okay, by this I mean that the complex is determined by the one skeleton, in the sense that a set of vertices is a simplex if and only if they are pairwise adjacent. Okay, every time we have a set of vertices in which every two are adjacent, this has to be a simplex. The converse also holds here. I mean, if we have a simplicial complex, which is clique, then it will be the independence complex of a graph, namely the complement of the one skeleton. So if we study independence complexes of graphs, we are studying all the clique complexes. Okay, they are the same. There are many papers in the literature in which some homotopy properties of independence complexes are studied for some classes of graphs. Okay, say cycles, forests, paths, whatever. And the idea is that we want to understand homotopy in terms of combinatorial properties of the graphs and vice versa. So in particular, triangle-free graphs have received some attention. So a graph is triangle-free if there is no subgraph, which is a triangle. And there is a conjecture, there was a conjecture of Alex Engstrom in 2009. He conjectured that if a graph is triangle-free, then the independence complex should not have a torsion in the homology in any degree. Okay, all these homology groups should be torsion-free. This conjecture was not open for long because in the same year, Jacob Johnson, he proved that for any simplicial complex, there is a bipartite graph such that its independence complex is homotopy equivalent to the suspension of the complex. Now, a bipartite graph in particular is triangle-free. Okay, there are no cycles or of any odd length. So, a suspension could have any homology group. I mean, we are just shifting the original homology of K. So, in fact, any finally generated abelian group could appear as the second, third, or whatever higher than two-dimensional homology group of the independence complex of the triangle-free graph. So the conjecture is really false. Okay, anything can happen here. And in fact, Jacob, he proved that if the other direction, if you have a bipartite graph, the independence complex is always a suspension up to homotopy. So he classified the homotopy types of independence complexes of bipartite graphs. They are suspensions. Okay, it's a big class, but this is it. So after this classification, if we go back to the original question by Engstrom, we can ask, okay, but what are the homotopy types of independence complexes of triangle-free graphs? They will contain all the suspensions, but in principle, there could be something else there. So in order to attack this question is that I introduced this notion of star cluster. So let me recall what is this definition. So if we have a simplicial complex K and sigma is a simplex, then the star cluster of sigma is just the union of the closed stars of its vertices. So this is a subcomplex. Let me go to an example. This is a two-dimensional simplicial complex. Sigma here is a two-dimensional simplex. So the star cluster is the union of these three stars. Okay, so in this case, is almost all the complex, just this one simplex is not there and this one simplex. Okay, so this is the star cluster of the simplex sigma. In this case, we can see that there is, I don't know, non-trivial H1, there is a hole here, okay? But if the complex is clique, this cannot happen. I mean, all star clusters will be contracted, okay? This is a generalization of the notion of star of a vertex. I mean, the star of a vertex is the star cluster of that vertex, and in clique complexes, all these are contractible. So this allows us to identify subcomplexes of K, which are contractible. And once we have these fundamental pieces, gluing this star cluster, we could have some homotopical information of the complex. So that is the big idea. We will see how it works in particular examples. So let's go to a possible proof of this statement here. I will prove something stronger, namely that if we have a collection of faces of a fixed simplex sigma, then the union of the stars of the simplices is contractible. So if we prove this, in particular, when I take the collection of zero-dimensional faces, we will have the star cluster. Okay, this is the definition. So we are going to prove this stronger because we are going to use induction, that's all. So for K equals 0, we have just one star, which is a cone, this is contractile. And for the inductive step, we will write this as a union of two things of the same kind. So by induction, each of them will be contractible. And in order to prove that the union is contractible, it suffices to prove that the intersection is contractible. Okay, so this is what we will check. The intersection of these two things, if I distribute, is exactly this thing here. And I claim that the intersection of two stars is the star of the union. In general, for general simplicial complexes, this is not true. I mean, there is one inclusion. The right is always included in the left-hand side, because if we have a simplex, which is in the star of sigma I union sigma k, it is certainly in the star of each of them. The other inclusion in general is not true, but it is true for clique complexes. Concretely, if we have a simplex tau, which lies here in the star of each of them, then in particular, every vertex of tau will be adjacent to all the vertices of sigma I and sigma k. But also the vertices of sigma I and sigma k, they are all adjacent because they are both faces of sigma. So by the clique property, we will have a big simplex, which is tau union sigma I union sigma k, and this says that tau lies here. Okay, so by the clique property, we have the other inclusion. But this thing here, this is again a collection of faces of the original sigma, and we have less than k plus 1. So again, by induction, this will be contracted. Okay, so we have finished the proof. This is the star cluster of a simplex is always contractible. And if we remember what we wanted to do, our motivation for this definition was to understand the homotopy types of independence complexes of triangle-free graphs. We know that they contain the class of bipartite, the independence complexes of bipartite. So by Jacob result, these are suspensions. Okay, and we wanted to understand whether there are more examples here or not. And we will prove that no, this is in fact an equality, that the independence complex of the triangle-free graph is always a suspension up to homotopy. Okay, are there any questions? Okay, I will go now to a proof of this result. Okay, we want to see that the independence complex of a triangle-free graph is always a suspension, homotopy equivalent to a suspension. And we are going to use this notion of star cluster that we just included. Okay, so let's go there. Take any vertex, okay, V. If V is isolated, then by the definition of independence complex, this will be a cone with apex in V. Okay, So this will be contractible. If B is not isolated, then I consider all the neighbors of B, and I claim this is independent because recall that the graph doesn't contain any triangle, so no two of them could be adjacent. So this is an independent set, and since V is non-isolated, this is non-empty. Okay, so this will be a simplex in the independence complex. Cool. So it makes sense to consider the star cluster, which we know it is contractible. The star of the vertex B, of course, is contractible. And I claim that the independence complex is the union of these two contractible pieces. Why is that? Because if we have a simplex here, I mean an independent set of vertices in G, which is not in the star of B, that means that when we add this vertex V, this set of vertices is not independent anymore. So that simplex has to contain one of these red vertices here. So it is in the star of such a vertex, and by definition, this is contained in the star cluster of N. Okay, so this is why we have a union, and every time we have a complex covered by two subcomplexes which are contractible, this is a suspension. Okay, a homotopy is the suspension of the intersection. Good. So this is one application of some version of the gluing theorem. Okay. Good. So we have a suspension, and we prove that this is an equality. So again, we have classified the independence complexes, the homotopy type of independence complexes of triangle-free graphs. In fact, here we didn't use that the graph is triangle-free. We used something weaker, and it is that there exists one vertex, at least, which is contained in no triangle. That is enough. Okay. So these are many classes of graphs, such that the independence complexes they are always suspension. Good. So this is the first application of this notion of star cluster, and there are many other results regarding independence complexes. At least we can that we can think with this notion. Concretely, there is a result by Kozlov. He understood the homotopy types of independence complexes of cycles. Okay. In fact, he used this result together with Eric Babson in order to give a proof of the Lovaas conjecture. Okay. So this is a step in, although he proved this in a much previous paper. So I think he used some ideas of collapses and shellability in his proof, but we can give an alternative proof of this fact using star clusters. Okay, so he proved that the independence complex of a cycle is always a sphere or a wedge of two equidimensional spheres, and this dimension depends on the congruence of n modulo 3. Okay, so our proof will be the following. So suppose that we have this cycle, okay, and assume for a second that n is greater than or equal to 4. Okay, it's not 3. So in particular, this graph doesn't contain triangles, and we can use the idea of this proof. Okay, so we are going to call this will be our vertex V. Okay, and the neighbors, they are these red vertices. So we already know that the independence complex of G is the union of the star of B and the star cluster of the neighbors of B. Okay, we are using this equality here. So in order to understand the homotopy type of this guy, we need, or we could try to understand the intersection. Okay, so because of this. Okay, so what is the intersection of the star and the star cluster of these two vertices? Well, if a simplex is in the star of the blue vertex, okay, it means that when we add the vertex n-1, we still have an independent set. So that simplex cannot contain any of these red vertices. Okay. On the other hand, if the simplex is contained in the star cluster of this simplex here, it means that we can add either this vertex or that vertex to still have an independent set. So that simplex cannot contain the blue vertex, and moreover, it cannot contain 1 and n-3 simultaneously. Okay, otherwise we are safe. So the simplices here, they are independent set of vertices in this graph, which are just black vertices, okay? And they do not contain 1 and n-3 simultaneously. So this is exactly the independence complex of Cn-3. Okay, it's a smaller cycle. Okay, and here we have the induction that we need. So this is homotopy equivalent to the suspension of this independence complex. So in order to obtain a Coase-Lowes result, we only need to consider the first 3 cases, say n equals 3, 4, 5, and that's it. So this is a complete proof of Coase-Lowes result. Any questions? Okay. So this is an example of a proof of an error result. And well, there are many other things which appear in the literature and also new results which can be seen with the star clusters. Another result of this type of classification of homotopy types by Ehrenborg and Hetier. So they prove that if G is a forest, then the independence complex is always contractible or homotopy equivalent to a sphere. Okay, and again, this is something that we could think using star clusters. A result by Peter Sorba says that if we have a graph and we take this subdivision, this is the barycentric subdivision of the one-dimensional complex. Okay, so it is for every edge, we subdivide this in 2 parts by adding 1 vertex in the middle. So this is G prime. And the independence complex of this graph is homotopy equivalent to the suspension of the Alexander dual of the independence complex of the original. Okay, so again, here we have a bipartite graph, and we will consider the star cluster of one side, which is independent, and the other side of the bipartite graph will be one simplex, and we will use the same kind of idea that we have here of covering with 2 subcomplexes which are contracted. There are other kind of results that we can think about. This is if a graph is claw-free, and by that I mean that this graph of 4 vertices, this is the claw. Okay, a graph of 4 vertices. This is not an inducer graph of G. Then in this case, we are going to say something about the connectivity of the complex. I mean, all the first homotopy groups, they are all trivial. And so what is the idea here? Well, in order to prove that, where am I? That this complex is this D-connected, the idea will be to take a simplex sigma of maximum dimension, so this number here. And then what I claim is that if we have a simplex tau, okay, which is small in the sense that its dimension is smaller than or equal to this number here, then I claim that tau will be contained in the star cluster of sigma. Okay, why is that? Well, because of this factor here, I claim that tau can be extended to one of the simplices of one of the vertices of sigma, so we still have an independent set. Otherwise, by the size of these simplices here and some pigeonhole argument, if this one was not in the star cluster, we would have a vertex of tau which is adjacent to 3 different vertices in sigma. And since sigma is independent, we will have a claw. This cannot happen. So I'm just giving a brief idea of the proof. Okay. So the idea is that this contractible subcomplex of IG absorbs all the small simplices. Okay. So the D-dimensional skeleton of IG is contained in a contractible subcomplex. So how do we obtain this complex from this contractible subcomplex? By adding high dimensional simplices. So the low homotopy groups will not change when we add higher dimensional cells. And this is why all the homotopy groups will still be 0, okay, up to this dimension. So this is more or less the idea of the proof. Some other results that we can think using the notion of star cluster is, so a result goes like this. So if we have any simplicial complex, then we can prove that there is a planar graph G such that K is homotopy equivalent to the independence complex of G modulo taking suspensions. Okay, there is some iterated suspension of K, which is homotopy to this where G is planar. Okay, so this is a different flavor of the result that we can prove. Okay, so these are just some applications, but probably today we are more interested about applications in about Vietoris-Rips complexes.
Sorry, just real quick. Any of that,
Yes.
any of this should work for infinite graphs also, right? I think at some point the graphs were declared to be finite, but
Yes, yes.
yeah.
Yes,
Okay.
in general, I work with finite things, but
Yeah,
I mean, I don't know for,
the star cluster is
for
still
any of
contractible, and yeah,
yes, it will still be contractible.
I think everything
Okay,
works.
I use induction, but there will be no problem there, right?
Right.
So this will still be contractible.
Yep.
Okay, so I will consider Vietoris-Rips complexes of sets. Again, I will think about finite sets, but probably many of these things, in fact, the conjecture that I will mention later, that probably you all know about, probably extends to infinite sets, but I will speak about finite subsets of the two-dimensional Euclidean space. And there is a result, I think it's from 2009, probably it was published in 2010, about chambers, the Silva-Erickson, there is a C missing here, so Erickson and Ghrist. So they proved that the Rips, the Vietoris-Rips complex of this planar set, wherever this R is, will be, the fundamental group will be free. Okay, so they prove something about the homotopy invariants, the fundamental group of the Rips complex of planar sets. And so, of course, a natural question is what can be said in general, okay, about the homotopy types, which can be realized by Rips complexes of planar sets. They give some information about the fundamental group, but perhaps we can prove something stronger. We can classify all the possible homotopy types. Okay, so this is the natural question. And when I read this paper, I was working with star clusters at that time, and I said, okay, then perhaps this is something that I can think about because a Rips complex is clique. Okay, and after all, star clusters speak about independent complexes or clique complexes in general. So potentially this could be useful. So if we want to understand the homotopy types, which can be realized by planar sets, we could try to find some examples, and it is not hard to see that all the spheres can appear here. Namely, if we take, I will fix this parameter R as 1, and if we take a circle of diameter 1, and we take an even number of points, in such a way that for every point, the antipodal point is also there. Okay, if you want, this could be the vertices of a regular 2 and 1. So I claim that the Vietoris-Rips complex of this is a sphere. Okay, just because any two antipodal points, they are not adjacent because the distance is exactly 1. And here I'm using, okay, it's strictly smaller than 1, and the diameter, the definition of the Rips complex. But every vertex is adjacent to all the other vertices in this circle. So what we have here is a cross polygon. Okay, it's the suspension of a zero. So in this case, we have a model of a two-dimensional sphere. Okay, this is an octahedron. And we can do this for any dimension. So here we have a three-dimensional sphere. And if we put this at an appropriate distance, so this one is slightly smaller than 1, we will have a wedge, in this case of S2 and S3, and we can have any wedge of spheres of possible different dimensions, and we can also have disjoint unions of this thing. Okay, so a natural conjecture is that, okay, perhaps this is all that we can have. So disjoint unions of wedges of spheres. Okay, so this is the question. Are there any other homotopy types that we can obtain for planar sets? Okay, so all these examples, of course, they appear, but can we have anything else? So, this is the conjecture. I believe it is still open. So let me tell you what we thought about with Martin Tancer back in 2010, 2011. I will recall the notion of this homotopy invariant, the Lusternik-Schneiderman category. So the definition is the following: X will be now any topological space. So a subset of X is said to be categorical if the inclusion is null homotopic. Okay, it's homotopic to a constant map. In particular, if U is a contractible subset, contractible subspace, then it is categorical. Okay. So what is the Lusternik-Schneiderman category of X? Is the smallest number n such that X can be covered by n+1 open categorical subsets. Okay, if there is no such n, the category is infinite. So let's go to some examples. When is the category of a space 0? We should be able to cover X by just one open categorical set. So it has to be X. So the inclusion, I mean the identity of X, has to be null homotopic. And this happens exactly when X is contractible. Okay, so this is category 0. What can we say about a one-dimensional sphere? Okay, so we'll wait for my pen. So a one-dimensional sphere, we know that it is not contractible, so the category is greater than or equal to 1. And of course, we can cover this with two open contractible subsets. Okay, this one and that one. So the category will be smaller than or equal to 1, so it is 1. And in fact, this holds for any sphere. Okay, we can take the complement of two points and the podal if you want, or any other, and this will be a covering by two contractible open subsets. And in fact, this holds for every, let's put something like this, for every suspension. Okay, if we have the suspension of the space, again, we can take the complement of this point, the complement of these points, they will be contractible, open, and they cover X, the suspension. So the category of the suspension is always 1 or 0 if it is contractible. Cool. Well, much more elaborated examples are these projective spaces, real or complex of dimension n. And this is the n-dimensional torus, okay, S1 times S1 times S1. So they all have category n. So in particular, the category could be arbitrarily large, even for compact serial complexes or manifolds. Okay, this could be arbitrarily big. This could be useful later. I said already that the category is a homotopy invariant. This is easy to prove. It's an exercise from the definition. Okay. In general, it is very difficult to compute the category of a concrete space. There are many papers that give some information for even a particular manifold. They say, okay, we have this lower bound, this upper bound. They are not the same, but okay. So this is the new result, and so it is something that is very hard to compute. Some non-trivial lower bounds are given by this homology invariant. This is the cap length of X. So the definition is the cap length of X is the greatest, the biggest number n, such that there are n elements in the homology ring whose product is non-trivial. Okay, so this is a homotopy invariant which gives a lower bound for the category. An upper bound, well, there is an upper bound which is given by the dimension, if you have a CW complex, but also for closed differentiable manifolds, we have this upper bound given by this clique X. So this gives some connection to Morse theory. For instance, this clique X is the minimum number of critical points of a differentiable map from the manifold into the reals. Okay, so for instance, if I take this height function of the torus, we have 4 critical points. So the category of the torus is less than or equal to 3. In fact, it is 2. Okay, there are smarter functions here that we can put in order to have just 3 critical points, not 4. Okay, so well, these are just some results in order to give you some flavor of course, this Schneermann category is. If we want to go back to independence complexes, we can say that if a graph is planar, then the category of the independence complex cannot be anything is smaller than or equal to 3. And a possible proof for this is, okay, if the graph is planar, we know by the 4-color theorem that we can paint with 4 different colors. Okay, by definition of coloring, each color gives an independent set. So this is a simplex in the independence complex. And since all the vertices are covered by some color, if I take the union of these 4 star clusters, this will be everything. Okay, so we are covering this by 4 contractible subcomplexes. And this is why the category is smaller than or equal to 3. Okay, here I am speaking about subcomplexes. If you consider an epsilon neighborhood, you really have an open set. And we go back to this definition with open sets. Okay, so, well, this gives some information about independence complexes, but we wanted to speak about Rips complexes, Vietoris-Rips complexes of planar sets. So the question is, what can be said about the category, the Schneermann category of these complexes here? Okay, is there any restriction? So we are going to assume that this is connected. If this is disconnected, okay, the category could be arbitrarily large. This is not interesting. So suppose that this is connected, and then we can apply this to each connected component. And I want to say something about this category, and this is the idea. Okay, if I wanted you to take something today, is this idea here. So suppose that we have a bunch of points in the plane, and the idea will be to subdivide the plane into squares in which the diagonal is slightly smaller than 1. Okay, 0.95 would be enough, but not something smaller. Okay, you will see why we need this thing here. And then take any square. Okay, so the diameter of the square is strictly smaller than 1. So if we take all the points inside this square, this will be a simplex in the Vietoris-Rips complex. Okay, so we can consider the star cluster of such a simplex. This will be a contractile subcomplex of R. Good. Now, if we consider another square, which is at distance 4 in terms of squares, but the distance is smaller than 4. Okay, so I move 4 squares to the right. I have another simplex. Okay, so we can consider these 2 star clusters. And I claim that they are disjoint. Because if we had a vertex which is in both star clusters, so in particular the distance of this vertex to each of the squares should be smaller than 1. Okay, and therefore the distance between these 2 squares should be smaller than 2, but no, the distance is bigger than 2. Okay, this is the choice of this epsilon here. Okay, so they are disjoint. That means that, so we have these 2 contractile subcomplexes, they are disjoint. And we are going to take more green squares. So we have this lattice, every 4 squares in horizontally and vertically. So we have infinitely many these green squares. And I claim then that if we take the union of all these star clusters, this is a categorical subcomplex of the Rips complex. This is because they are disjoint. Okay, pairwise disjoint. So this inclusion, so this is R, this inclusion is null homotopic. Okay, each of them is contractible and they are disjoint, and this one is connected. Okay, so this is null homotopic. So this is one categorical subcomplex. Now we continue in this way, we take a different color, and we have another subcomplex which is contractible. And if we want to go with this pattern here, we will need 16. Okay, with 16 colors, we can prove that the Rips complex can be covered with 16 categorical subsets. So the category, the Schneermann category, will be at most 15. Okay, so not everything. This is a non-trivial restriction to the homotopy type that can appear for this planar set. Okay, not anything can be there. We have this, and with Martin Tancer, well, he's a specialist in this in general, in many things, but in Euclidean geometry. So he really improved this idea of this tiling with squares. So he began with the hexagonal tiling, this regular tiling by hexagons. This was not good enough for applying this idea, but he changed these hexagons in some particular way and used the same idea to cover the Rips complex with 10 categorical subcomplexes. So we have a better round, which is this number 9. Unfortunately, this idea as it is cannot be improved much. I mean, what we are doing here, we are covering by different colors, and we want each piece of these colors to have diameter smaller than 1, and we want the distance between any two of these pieces of the same color to be greater than or equal to 2. So we cannot cover with really fewer colors. Okay, I think that there is a bound with 6 or something like that. So we cannot improve this much with this idea. Okay. However, what we wanted to prove, the conjecture says that we should have always a wedge of spheres if it is connected, and a wedge of spheres is a suspension. So we know that the category has to be 1 or 0. So we are still very far. Okay. And this is why, even though we believe that the idea is very nice, the result is little weak. And this is why we never publish this result. Okay, so this is the idea. So the natural question is whether we can improve this. So perhaps we could arrive to this one here, or just improve this by using some different ideas. Even if we prove that the category is 1, we are proving that we have a suspension. So this is a nice result. But still, in order to arrive to wedges of spheres, there is something else to decide. Okay. Well, so this is what we did. This is what I wanted to tell you about. I just recall that there are later but published results. So Barmak and Henry, so they prove that the conjecture does hold when this set is not in any place in the plane, but inside a circle, I believe, of radius 1. So in this case, the homotopy type is the one of a sphere, of a wedge, or a wedge of spheres of the same dimension. And Michał with Florian and Bakili, so they prove that if this Rips complex of this planar set has a particular shape, it is a normal pseudomanifold, then it has to be a sphere. Okay, we cannot have other classes of manifolds. Okay, but if we care about the homotopy type, so well, this doesn't say anything about the possible homotopy types of manifolds which cannot be there. Okay, we have this this strong hypothesis on the combinatorics of the complex. Well, I think that's all I wanted to say.
For a great talk, and let's please unmute ourselves to thank Jonathan. All right, are there any questions?
Are the intersections of these star clusters anything nice?
No, it would be great to know that.
Okay.
In general, I don't know, and it is a key question if we want to understand what happens here.
Yeah.
Okay, and I know some ideas. We have to use some properties of the plane. Okay, and I don't know. I don't know how to use them, but for sure there has to be something in order to understand exactly what you're saying. What are the intersections? So this is key. I don't know.
No.
I had maybe a short question and then a quick comment and a longer question. So the short question, I really like this bullet you have there that if G is a planar graph, then the category of the independence complex is at most 3. And you gave a nice argument. I mean, this argument furthermore proves that for any graph, the category of the independence complex is bounded by the chromatic number -1. Is that right?
Yes, exactly. What you're saying, yes.
Yeah. The comment, fantastic talk and fantastic work. I'd be super interested if you ever reconsider and were interested in publishing. I think there's an audience for this result bounding the category of these Rips complexes of planar points. So, you know, when talking about this conjecture with people, so the result that the fundamental group is free, that rules out things like the torus. S1 cross S1, right? But it doesn't rule out things like S3 cross S3, right? And so I was curious, what is the category of something like S3 cross S3 or S3 cross S3 cross S3? Because your result is ruling out lots of examples along those lines, products of higher dimensional spheres that otherwise aren't ruled out by any results I know of.
Probably it should be easy to understand, at least have a bound for a product. I mean, S3 can be covered with 2 contractible subsets. So what can we say then about the product? This torus S3 times S3. I don't know, at least 4 should be enough, but can we do better, this product? Probably, I don't know if we can do better, but perhaps looking at the cohomology, it should be easy to say something with more copies. I mean, with 2, 3, 4, probably we cannot rule them out with this result of this bound 9.
But once you get an n-fold
more copies, perhaps that is, at least I remember this result that I recall that for S1, which we are not interested because of the fundamental group, S1 is not interesting here. But if we take the n-dimensional torus, the category is n. So this is really increasing when we take more copies. For S3, probably the same argument works, but I don't remember now how it is proved, this lower bound for the category of the torus probably is using this cap length. So if we understand the cohomology ring of this S3 times S3, etc., perhaps already we can prove that the cap length is already big enough, and that should be enough. Otherwise, to find other lower bounds, it is hard. But perhaps cohomology is good enough for this example. But it is something that I will have to check. Perhaps I'm saying something which is not working for some tree.
No. Yeah, but yeah, yeah, it seems like for a large enough product of 3 spheres, you're going to be able to rule that out as a possible.
Probably.
Yeah. Very cool. Thank you so much.
Something else just occurred to me. I guess that the same idea shows that for any n, I'm not going to say this right, for any n, there's a uniform bound on the category of the Rips complex of something living in Rn, right?
Yes, exactly. What we did here with squares, you do it with the hypercubes and exactly.
And it would be bigger, but it'd probably grow exponentially, even maybe. I'm not sure, but
apparently, yeah.
But still a uniform bound for each n. So that's kind of interesting.
Yes.
Too. Yeah.
Any more comments or questions?
Maybe just a comment or question. So I think any graph can be realized as a unit disk graph or the one skeleton of a Rips complex in some high dimensional Euclidean space, right? So take any graph, you can realize it as the one skeleton of a Rips complex in a high enough dimensional Euclidean space.
Yes.
For more complicated graphs, you're going to need higher and higher dimension. So I'm curious now how. Okay. Finite graph, yeah. And so I'm curious now how that scaling might compare to the scaling that Matt was just alluding to on the category as you increase the dimension.
Sorry, come again. So you want to understand, you want to give a lower bound for this dimension that you need in order to embed this graph, or?
Yeah, I suppose, looking at the category of Rips complexes in, 3D or 4D or 5D, right?
Yes.
That might be a way to say, here's a given graph. I know it can be embedded as the one skeleton of a Rips complex in some high dimensional Euclidean space, but here's a way to prove that that dimension of that Euclidean space needs to be sufficiently high. Maybe you can prove that 5D won't work, but you need at least 6D.
Okay, perfect. Yeah, and I get it. Okay, good. Yeah, you could have a result in that sense. Sure. Yeah.
Do you think it's okay? So in the plane, the fundamental group has to be free. What about in 3 space? Is there just no restriction? I think in 4 space.
Fundamental group, I don't remember. So this paper, they did exactly, well, in the original paper, they speak about dimension 3, 4, and I remember that this paper here, they speak about so there is this map that goes from the complex into what they call the shadow. Is when you see the projection of this complex in the original Euclidean space, and they study the connectivity of this map. Okay, if it preserves the homotopic group until certain dimension, and I know that they have results exactly for dimension 3 that were open before.
I think once you hit 4, there would be no restriction. I think you can embed any 2-dimensional simplicial, any finite 2-dimensional simplicial complex in, or at least you could get every finitely presented group that way. 3 dimensions, I don't.
I think, I don't know. If you want, so dimension 4 is enough. I know that dimension 5 is enough. So dimension 4 is also enough.
I thought dimension 4 was enough, but I could be wrong. I guess I was just curious if your stuff could somehow recover the fact that in the plane it has to be pi1 is free, and if so, then what would it say in dimension 3 also? But I guess I'm not.
I think, yeah, so in dimension 3, the fundamental group that you can get is just the fundamental group of any complex of dimension 3. Not
right.
More. So probably you cannot get, I don't know, C2.
So you don't think you can embed RP2 into, can you embed RP2 into R3? I don't know, actually.
R3, no.
Really?
No,
okay,
R3,
never mind.
no.
Yeah, okay.
So there is some restriction, and I think this is something is proved that this map that I told you that goes to the shadow, this preserves is an isomorphism in the fundamental group. So you cannot have everything, and this is the restriction. So they are the same homotopy, the fundamental group that you can have for 3-dimensional complex.
I just think it'd be interesting if your stuff could somehow recover the fact that pi1 has to be free in the plane, and then if it did somehow work, you could see what's happening in dimension 3. But
yeah, I don't know about an alternative proof of this
I don't know,
freeness of the fundamental group, even for the plane. I mean, what they do is the argument is very delicate, and they really explode the geometry of R2.
Okay.
I remember they have many lemmas, and they say, okay, if we have 2 segments that intersect, then the distance, I know this should be a cone. And there is really a precise list of lemmas that they need to understand the edge path group and prove that is free. And I don't know about a simpler proof of that.
I've never read the proof, and I think that's why.
Okay, I think when you read the first lemma, you say, okay. So this is what they are using about the plane. It is very smart, and it gets more and more complicated. And then it's just understanding the fundamental group combinatorial edge path.
Okay, well, thank you.
Right. I'll stop recording now, but if people want to stick around and continue chatting, that's fine.